Hi, I'm Dave. I'm going to do a talk about hacking retro games machines. So, what do I mean by retro games machines? Amongst us, many of us, when we were younger, we had lots of different computers like the BBC Micro, Commodore 64, ZX Spectrum, even the old Humble Oric. And some of you a wee bit older than that may have had consoles, like various different console machines like these. Of course, I didn't. My parents had no idea about computers, and we had something called a Sharp MZ700, which was absolutely useless. No games at all. So, 20, 30 years after these machines, because of the prevalence of emulators, everybody started to go, "Oh, wasn't the Spectrum good? Let's allow people to replay some of these games on the Spectrum and the C64. So people did, and the machines are being brought out. And it's reminded us basically how shite most of them were. So, I must admit at some points I spent literally days playing Laser Squad on an emulator. So I'm probably in that geeky section. So, and this is an interesting tweet that came out a couple of days ago, which means that officially the Xbox 360 is retro, which is quite scary. So what am I going to talk about? So these are some of the machines that have come out. So there's a ZX Vega at the top, the Mini C64, the PlayStation Classic. This talk's basically about an investigation of how these work, what sort of things you can do with them, and sort of basically just a little story about how I went around accessing them. Why is this important? It's not really. There's going to be no game-breaking security vulnerabilities here. None of them are internet connected. I did this just for fun to see where I could get and, where I could stop and what sort of interesting flaws there were in these sort of things. So I'm going to start off with the ZX Vega, which is where all this came from. So I was talking with a mate of mine and we just wondered how on earth it would be implemented. So first rule of reverse engineering is think how you do that yourself. So the theory we use is it'd be like some form of Linux and embedded Linux, and it'd be running an emulator. I'm not going to get into the politics behind this because there are lots of politics behind the ZX Vega. If anybody's actually read anything about the Vega Plus, I'm not going to get into that because everybody was wrong as far as I'm concerned. So I'm going to have a quick demonstration here. Here's a video that I recorded. It's through an HDMI to RCA feed, so it's a bit flaky on some of the images. I'm just going to demonstrate sort of what the Vega looks like. So they did a good job of making it look a bit sorry. Spoilers. No, sorry. There should not have been music on that. When I recorded, I ended up with my actual music playing in the background. So there's bits where I sped up the video and the music speeds up and slows down. I should have muted it. I do apologise. Imagine a chip tune in the background. It sounds like it's playing off a ZX Spectrum.
I'll second.
Oh, hold on. Do it really helps if I actually put that on the screen. You can tell I'm not an expert at this, can't you? It's the first time I've put the videos in my talk, so this is something I have not tried before. Right, let's just play that. So they've sort of matched it. You've got a twinkly little Spectrum-like chiptune in the background. I'm currently pressing this using a pair of tweezers, which is because I've taken it apart. So you can go through, you can load up a game, select your controls. And here's 1994 is the first in the list. And here I am potentially trying to play it. Nah, it's a bit shitty, really. So let's just reset that. One of the other features it's got is you can load custom games from an SD card. So here I am just loading it from the SD card. And here's a little bit of code I made in advance. And I'm just going to load this up. That took me 4 bloody hours to write. I could only get in the memory 5 frames from a GIF that I stole. So I'm sorry, that was a gratuitous joke. So anyway, how do we sort of investigate these? We can look at various different areas. We can look at the firmware, we can look at the hardware, and we can look at the software around it. So normally, before I even buy one of these, I start off by looking at the firmware. We're going to go into reverse engineering here. I hope you like hex dumps. Because I love hex dumps. So the first thing we can see from this is a hex dump of the header. We can see a copyright statement with a version number and what looks to be a date of release. And we look a bit further in, we can see a magic number which says Vega. We can see, you know, that's the date in binary format, so obviously it can make an easy check, version number check, and basically the size of minus the size of the header. Where are we going? Oh, yeah. And that's basically the rough structure in the C-like fashion. So go a bit further down, we have what's called an SMEM header. So this is based on IMX233, and that's directly from the datasheet. It doesn't tell us anything. It's basically what it uses when it boots the system from SPI. Also, we've got this thing called an STMP header, which is specific to the IMX233, and there's a tool around called SB tool, which allows you to dump it. The important thing to see from that one is the default key is not valid for this encrypted boot image. It's encrypted. Bugger. I can't actually read the damn thing by default. I have to go a bit further in. So anyway, let's have a quick look at the hardware. Here is the whole board. Our main components, we have a CPU, which is an IMX233, which is a very complicated device and stupidly expensive. But it does audio, it does graphics, it does the whole work. It's basically a computer on a chip. A bit of external RAM and SPI flash, which is where it does long-term storage. On the back, we have 3 lots of headers. First thing you obviously try and do is read the SPI flash. So here's an attempt of me trying to read it. I wrote some scripts to write SPI flash ROM would not read this, which is your normal technique. So this is me just dumping the SPI RDID, which is your read identifier. And that's my chip reader trying to read the data. I had to sort of mangle it because it's not quite right. And we dump it. It's exactly the same as we saw on the firmware image, so it's encrypted. Bugger. So next thing we've got to do is try and map these out. So I don't know whether anybody's tried mapping out test points before. So something you use a multimeter. It goes on to basic, you can use continuity tests and just see where pins go. We know roughly where the ground pins are, and we can just map those out onto the actual chip. And we can map those out into all the various points. I don't know how well you can see that. Yeah. And also we've got a 5-volt one, which interestingly only goes to the top header. So let's have a look at junction 4. Sorry, junction? Test pad 4. I'm not saying what the J stands for. Jumper. Yeah. Jumper. So in there we have ground, what we already knew about. Then beeping around we have, come on, show up. We have basically UART transmit and UART receive. That's a UART header. That's something I'm going to come back to later because it's going to be really useful. General rule of thumb, always look for UART because it's generally an easy way in. Jumper 3. Junction. Why do I keep saying junction? We can map again ground out. We can map out, it maps to something called the debug, which is an SJ tag header, which I'll go into later. And basically a voltage reference just so that it can work out what it is. So overall, oh yeah, final one. We already marked out this. Now, there might be some similarity. If anybody's done any hardware looking, that header is very familiar. In fact, it's very similar to a USB micro B connector. So presumably it's a second USB port that's been used and they've just not sold it to. So we can sort of, sorry, my words are gone now. We can, again, do a continuity test, map those out, and we can see USB data plus, USB data minus. It's a USB header. Yay! So here we are. This is how everything's mapped out. So we have all our test paths known roughly. I don't know what the top 2 ones in the USB header is, and the other one's meant to be deliberately meant to be floating. It says it's an on-the-go pin, so that says, is this a host or an actual central bit? So let's have a look at UART. This is what you got on the UART. That is not what I was expecting, to be honest. It must be a little sort of internal joke with the developer, but it tickled me. It's actually quite useful because even though I got no shell from it, error messages were dumped to that screen, which I use later. So let's have a look at USB. I didn't have a micro USB header, and I could have ordered one from Farnell, but I'm lazy, so I just soldered my own. That's sort of the high quality I used. Unfortunately, that USB was not active, so I couldn't do anything, but it was a secondary way of powering it. So the next one to go for was the SJTAG. Now, SJTAG is a weird system. JTAG is a way of basically it's a way of talking directly to the CPU. And you can do various different things, read the memory, potentially read flash. There's a cut-down version called SWD. This is SJTAG, which runs off one line, and it's got a lot of custom things in. So the only board I could find that would read SJTAG is this Olimex board here, this red thing. But fortunately, it worked quite well. So this is what my desk looked like while testing this. I'm ignoring the drinks can in the background behind the monitor. But so essentially, I've halted the whole thing there, and I was just trying to read everything. Running off a USB hub, so I could just turn things on and off as I needed to. So you can connect to it with a program called OpenOCD. It's a generic JTAG connecting thing. The program which will just talk JTAG, and it will pass anything down and will do all the hard work for me. So I could telnet in there. I can halt the device, and then I can read the registers, and it might not seem anything to it, but PC register 15 at the bottom, that's something that's roughly in the right area of memory. So I know it's running something. So that 0hex4000 is RAM in the memory map. I don't know what's called dirty, but maybe it should wash. So we can start dumping stuff from here. This is on-chip SRAM, which is static RAM that is stored within the chip itself, and I can read information from here. What I can also see are these, what I've highlighted in red, are basically showing me this is ARM code. E is the code for always execute, so I know that's 32-bit ARM. And that's a familiar string, which is starting to get really quite irritating now, seeing that everywhere. Going a bit further, we have on-chip ROM at the top, which is basically the bootloader. I found an interesting little string in there. The last sentence, no pygmies were harmed during testing, really. So somebody in Sigmatel must have found themselves really funny. So I can dump the on-chip RAM, and now we've got, my notes are wrong here. So I can now dump the RAM, and once I've dumped the RAM, I can load it into, in this case I use GCrypt to actually try and disassemble it and read it. I can see that it's roughly right. It looks okay. So I've got full access to RAM. The problem is I can't access flash because it's not memory mapped. If you can look on the memory map on the left side, it's not memory mapped. There's a whole set of way of doing this in registers. I could potentially map it out, go full WAID on it, and actually try and decrypt everything. But I took the lazy way. I made sure an emulator was running, then I dumped RAM. So in theory, the emulator must be in RAM to run, otherwise things will go a bit pear-shaped. As I said, so I was searching through just to see whether it was running. So here's a hex dump of the 48K Spectrum ROM, and here's a hex dump of memory. So as you can see, the bytes match up. This is basically the whole ROM. I know it's in there definitely. So my assumption is to see what the emulator is. Now I couldn't work out what this was. There's no artifacts in there to say it's fuse. Give you a hint, when we sort of look at these sort of things, when we say artifacts, we mean strings. Because we're lazy. We grep for those. I could not find anything to do this. So I need to have a look at the software. So first thing is try a few Linux breakout tricks. So try inserting commands and so on. So again, it's not giving me anything. This suggests it's not running Linux to me. It's running a raw ARM device, and they've got some sort of mapping of file names. So we need to go a wee bit more in depth. Can we actually find information within the emulator itself, like a debug mode or anything like this, or anywhere fingerprinting the emulator? So let's go back in time. Here is a die shot of a Z80 CPU. This is the physical silicon that it is based on. There's one important bit here, which I'm going to concentrate on. These are the registers, so that are within the Z80, and this is the physical bit of silicon that is those registers. So, again, back in history, Z80 has many registers. It's got a whole load of different registers, A, F, B, C, D, E, H, L, which can be used as 8-bit or 16-bit. Don't ask why it goes from F to H. I have no idea. Somebody made that decision. So it's accumulator flags, and then the rest of them have specific units. There's a set of clone registers they can swap between. And we have the index registers that we can use to load, do lookup tables. Program counter, interrupt register, and there's something interesting here. So the Z80, most of the emulators were written, Spectrum emulators have existed since like 1990. But in about 2000 and, I did take a note, mid-2000s, I think it's 2003, there was some evidence working on the die, and it's found out there's a hidden register called WZ. So WZ register is if you, so it's the Z80 is an 8-bit machine. If you try and load, say, a jump, you need to load that jump address into somewhere temporarily. That's what the WZ register is used for. But what we can know is if that WZ register is implemented in the emulator, then we can date the emulator and we can roughly work out when it was written. So here is a bit of Z80 code, which will attempt to read bits of that WZ register. So there's a bit of a bug in the Z80 is that the flags register will have bits 3 and 5, which are unallocated, will be bits 11 and 13 of the WZ register. So what I'm doing here is I'm priming WZ by doing the load BC, and then I'm trying to read bits of it back from the HL into the flag register, which I push in the stack and do all sorts of weird and wonderful things. So that's the code written in Spectrum Basic. Again, that's the first Z80 I've written in like 25 years. It's far too long to write. And here's it running on zx.spectrum.net, which does implement the WZ register. If I ran that on a real Spectrum, that's also what you'd also get. Here's it running on Fuse, which didn't at the time implement WZ. So what happens if you run on a Vega? So we're going to get something similar. Now, that's crappy code. That was just lazy and written out. There's a load of test suites for this, one of which is called Racksoft suite, which tests for something called mempointer. Mempointer is another name for WZ. So running this on a real Spectrum would get a list of tests and they will all pass. Running it on a Vega, I get all fails. So these are consistent with WZ not being implemented. What does that mean? Does it run Fuse? I don't know. It might use the same Z80 core. That's exactly what happens on JS Spectrum, which is a Spectrum version that runs on JavaScript. That's what it happens on Fuse. So it's about 90% certain that it is. So unfortunately, that's as far as I could get on the Vega. I can potentially edit the RAM, but I've got better things to do. So there's only so far you can go before you spend far too much effort on something that's not unimportant. Let's go on to the Mini C64. So this sold a lot better than the ZX Vega because it went to the US market as well. It's done by the same guys, just in a different company name because politics. So again, let's go into the firmware. And we can see, oh look, another hex dump. First thing that jumps out to anybody who's done reverse engineering is that ELF. So that's the header for a Linux executable there. And also 28 tells us it's ARM. So all useful information. We can see a pointer to that and a potential size of file. And of course a header, which I didn't see at first, but of course AC64. AC64. I literally hit myself when I saw that. So we got again something that's that's the size of the file. Don't know why it's repeated twice because I'm trying to guess all this. And we've got something else that could be like pointers to other chunks of data. And that big chunk, there's 16 bytes of data, which I have no idea what it is, but it looks very much like a SHA-256 hash. So I'm assuming that it is, and therefore it does some form of signing or check-in. So anyway, let's throw that into a disassembler. And way of cheating when reverse engineering, look at the strings. So we found this GCrypt cipher set IV, which is a function call within GCrypt, which gave a bit of hint so I could actually look through for the different things, follow it through, and map out various different function definitions. And we can see here, it encrypts the data, and we can see that it sets a key and it sets an IV, so it's obviously decrypting it. And that's a bit of code that sort of works out the key. I sort of looked at that. This is Gidra's decompiler. It's not brilliant, but it sort of works-ish. And I went, I can't be bothered with all that maths, so I'll do it the easy way. There is an easy way of doing this. We can just run the executable. Of course, I don't have an ARM development system. You probably do. But it's like, I'm feeling too lazy. But there's a lovely little hack called QEMU. So QEMU is a multi-emulator of various different things that's free and open source. And the nice thing about it is you can run a command under QEMU where it starts up in its own little sandbox, run the command, and then drop you out. And it looks like it's a normal command. So this is roughly, init cipher is where we know that the key is. We have a start address, which is your address within memory. And we see these two parameters, which are name key and IV. So we'll store those in register 2 and register 3. So I've got another video here. I do apologise. I have typing errors in this, and I'm not very good at typing on when I'm being recorded. So I'm just going to run QEMU here. Just realised how small that is up there. So I'm going to run it with a GDB session, so I can actually do a debug on it. So I'm going to single step through so it doesn't just run it. And then I'm just going to run my executable. And then in the other window, I'm just going to run GDB, connect back to it on port 9000. So it's now paused. I'm going to put a breakpoint in at that, remember that address. Run the program. Type an error. And now I'm just going to dump those two registers. By the way, this was about my 10th effort to record this. So, and there we have basically the key and the IV that we can use to decrypt content. Now, it's silly, I could use that to decrypt it, but at this point I did what I should have done before and did an internet search and see whether anybody else had done anything like this. Nobody actually looked at the firmware. People have looked at the hardware, and there was an easier route in. So here's the board. There's a header down there, which is a 4-pin header. Which unfortunately I didn't take a photo before I soldered some headers on. So they're just some headers I just soldered on. And those are headers for UART. So, and there's two buttons here which are reset and fell, which is, so it's got to run an all-winner chip in the center. And those are, it's certain mode called fell, which basically accesses the bootloader. So, if we go on to UART, oh look, we have a Linux shell. And it's Sun XI, which is an all-winner, basically version of Linux. It's all set up to run from Linux. But we don't know the password. We have no idea what the creds are. So, can we get a bit further in? If you notice, there's that button, hit any key stop autocorrect. So, let's do that. And we're now into basically the bootloader. And we have the boot command there. And we can go in there and we can basically, by putting RAMFS onto the end of it, we can boot using a RAM disk. So it just boots into a RAM disk. There's no password on it. So we've got a rough shell here. It's not running the full operating system because it's not mounted. It's just running on a RAM disk. What we can do is mount the actual operating system in properly, and we can see the root password there. I don't know what that root password is. I've tried cracking it. I gave up after 2 days because just nothing was coming out. So there is a lazy way of doing this. We can just change it with that little line of said there. I changed the password there to password because I'm not very creative and I forget difficult passwords. So just doing a bit of said just changes the password for me. And now I've got full access. At this point, it was, I ran out of time. I was suggested I should put a BBC micro emulator on here just for fun. But, it's one of those, it's actually quite difficult to do the cross-compiling chains and get everything working. So, That's sort of it. There is that's a URL to my blog. There is some articles about this which relate some of the work on it in a bit more detail and some other random stuff, but I'm not a very good blogger, so it's like 2018, I think, was the last one I uploaded. Any questions? Anything still awake? Yeah.
Have you looked at the C64 Maxi or whatever it's called?
Yeah, that came out just before Christmas, and I couldn't get hold of one. I've seen a few videos where there have been teardowns of it. The board is similar, but not the same. So I wouldn't say that it's probably going to be the same. They might have fixed it. I don't know. Yeah, there are other ones. I mean, there's a same UART console hack for there's PlayStation Classic, which I just it's one of those ones I didn't actually have time to do. There's also a hidden escape menu that you can do from the emulator. If you plug in a USB keyboard, you can actually get the and press escape. You can actually get the console, but only certain USB keyboards work, and none of mine did. And I'm not paying 90 quid to buy a keyboard just to test one thing out.
Is there any common denominators between all the boards?
No.
Like, no?
No.
Or is it just you see what's there and take it as it is?
Yeah. So the Vega one is pretty much a reference design for the IMX233. That All-Winner one is pretty much it's a tablet board basically. The PlayStation Classic is a tablet running Android. So there's a load of them, and there's levels of, because people are rushing to get them out for Christmas to get the retro craze, which is currently in. Everybody they just put these things out. They do sort of like the minimum things and try and get it out. Yeah, basically. So there's not really anything. Everybody's doing it their own way. It's so easy to buy a single board computer, put Linux on it, put an emulator on. Then you can just do it however you want, or whatever you design your guys know the best.
You know the bit where you used Cameo to run the ARM binary?
Yeah.
Would it have worked if you just run it on a Pi?
Yes. But that would have required me to copy it over to my Pi.
Okay.
It might have, the other thing as well is it might have done, it may have worked, it may not have done, because it depends on exactly what libraries were linked and what requirements it was. And I just like that QEMU technique.
Oh, yes.
It's brilliant. I just wanted to show that as a demonstration, that as a technique itself, because you can run that with any other CPU you want. So there's MIPS, there's PowerPC, there's even like PA RISC and stuff. Weird and wonderful. Right.
How much faffing around did you have to do to get the debug thing working?
Lots.
Yeah.
Yeah. What I missed there is the story of me getting it working, and that includes a 6-month gap as I angrily threw the board away and then found it recently and went, I probably ought to retry this.
I was going to say, has anybody ever actually plugged into a JTAG header and had it work first time?
No.
And the answer is no.
No. I do this professionally, and yeah, still no. It's like half the time it's like JTAG test. Oh, ID code for success. Oh, it doesn't connect. But now it does. Why?
Or connects and won't break.
Yes. Yeah. Or you can't halt it.
Yeah, exactly.
So there's various different things. So you can't actually debug the CPU unless you halt the CPU. So you can't get loads of things like registers and dump the memory. But sometimes you can get into the JTAG, you're all successfully connected, you can't halt the CPU. Oh, just time to run upstairs for Mark. So downstairs.
Yeah, all right.
Cool. Thank you.
Thank you.